Hey everyone, so in this video, I'm going to walk through some of the questions and concepts from the exam to study guide. So let's get started. So on the exam, you will have a question related to random variable matching. And so we learned in chapter 5 that we can have a discrete random variable or a continuous random variable. And the key thing that you want to be thinking about when you're working on a question like this is whether it is countable. So I like to use my hand, and if it's a situation where I could actually count it on my hand, then that would be a discrete random variable. So in this first problem here, we have the number of people that vote by mail in the upcoming election. So we know that people, we can count the number. So 1, 2, 3 people, etc. And so we know that this is a discrete random variable because it's countable. Now in the next problem here, we have the average speed of cars driving on campus measured by radar equipment. So you really can't count the speed of cars, and the average speed of cars could be on a continuous scale. In theory, it could go up to infinity. We know cars have a maximum speed limit, but for example, let's say it's 22 miles per hour. You can't count 22 miles per hour. So this is going to be a continuous random variable. The average time taken on exam 2 measured in Canvas, this is another continuous random variable because everybody's time could be different. It could be 60 minutes and 30 seconds, 70 minutes, etc. So you can't count the time taken, so that's a continuous random variable. And then finally, the number of car accidents on campus per day. That is a situation where we can count these because I can count there was 2 accidents, so 1, 2. Or there was 4 accidents on campus on another day, so 1, 2, 3, 4 accidents. So that's gonna be a discrete random variable. Next up here is probability distribution matching. So on the exam, there'll be a few questions where you will be presented with information about a situation and you need to identify which probability distribution applies. So we learned about 4 different probability distributions: the binomial, uniform, exponential, and Poisson. So one thing I want to emphasize here is we did skip the hypergeometric distribution. I made that content optional. So that will not be on the exam. So let's walk through the problems here and identify the applicable probability distribution. So the first one here is the number of people that vote yes on a proposition in an election poll. So that is the binomial distribution. And the way I like to identify whether it's binomial is you only have 2 situations, either true or false, yes or no. So I like to think about like a bicycle has 2 wheels. So if you're dealing with a situation where it's just 2 outcomes, that's going to be binomial. So in this case, on a proposition in an election poll, you can only vote yes or no. The next one here, Apple sells an equal number of all 4 different models of AirPods. So we see a key word here and we see equal. So if you see something like this in the problem, this is going to be the uniform distribution because it has an equal number across all models, so the distribution is equivalent. Next up here, we have the time between crashes for a laptop. So whenever you see a situation in the story here where it talks about identifying the probability of something occurring between like 2 events, that's going to tell you the hint that this is an exponential distribution. And then finally, the number of text messages received per hour. So this is going to be the Poisson distribution. And the way I like to identify when this distribution applies is you will often see a keyword of per hour. So we want to know the probability of getting a certain number of text messages received per hour. So P for Poisson, P for per. So look out for that in the problems. When you see per, you should be thinking Poisson. So next up here, we're going to talk a little bit about the 2 discrete distributions, binomial and Poisson. And before we work through the problems, I wanted to talk a little bit about the decision process for what x do we use in the Excel function. So please note, for the binomial distribution, it is referred to as the number of successes. So binomial is yes or no, or success or failure. And so we are equating the number of successes to the x variable of interest. So what I've done here is I've have 5 different situations and in a way the problem could be worded. So the wording is so key here when you're making a decision on these discrete distributions. So the first one is the probability of exactly 4. So this one's going to be very easily, the x is going to be exactly 4. So whenever you see exactly, you're always going to just use the number that's given in the story or problem. The next one here is probability of 6 or less. So we learned in the lecture videos that Excel does the cumulative distributions from left to right, and it's going to include the number all the way up to x. So if you see a problem like probability of 6 or less, we know that we're going to use 6 as the x in the function. Here we have a problem that's a little bit tricky. It reads the probability of greater than 5. So I like to think in my head, I'm going to reword this. Greater than 5 is technically the same thing as saying 6 or more. And we know from the lecture videos that Excel will add up the probabilities up to the number that you are indicating in the function. So probability of greater than 5 is going to be 5 in the function because we are calculating up to 5, and then we're going to use the complement rule, 1 minus that number, and that would actually give us 6 or more, or the same thing as greater than 5. Here's another one that's tricky. So the probability of 9 or more. So we know that we are looking for 9 or more. We want to use Excel to calculate up to 8 so that when we use the complement rule, we will be getting 9 or more. So this is one of the examples where the x in the story is going to be 8. So 9 minus 1, so we calculate up to 8, and then we use the complement rule to get 9 or more. And then finally, probability of less than 7. So here's another one where it doesn't include the number. So the same thing as less than 7 is 6 or less. So the x in this one is going to be 6, which is the same as number 2 here, probability of 6 or less. So you can see that just based on the wording that's used, it's going to determine which x you use. All right, now that we've gone through some examples of what x to use, let's work through a specific problem related to the binomial distribution. So we have a problem here where it states that the USPS claims that no more than 9% of all packages arrive at the address late. So you're going to be assuming the binomial probability distribution here, and we have a sample size of 30 packages that were selected randomly. So in the story, we have P equals 0.09, that's our probability of success, and then we have our sample size, or N, equals 30. So we want to first calculate the probability of exactly 2 packages will be late. So we're going to enter equals binom.dist. We're going to enter 2 for x, or number of successes, 30 for the sample size, 0.09 for the probability of success, and then we're going to use false because we're dealing with exactly 2 packages. So we want to get the probability of exactly 2. So this will be false for cumulative, and then we get 0.2513. So here in B, we have the probability of 3 or less packages will be late. So we're going to enter binom.dist, and we're going to use 3 for the number of successes, or x, because we are interested in 3 or less, so it's including 3. And then 30 for sample size, 0.09 for the probability of success. And now in this problem, we want to use true for cumulative because we're calculating the probabilities up to 3 or 3 or less, and we get 0.7175. Then in the last problem C here, the probability of 5 or more packages will be late. So this is going to be 2 situations here that you need to consider. Number 1, we need to use the complement rule. And then number 2, for x, we are going to be using 4 because we're interested in 5 or more. So we first need to calculate the probabilities up to 4. Then the sample size, again, will be 30. The probability of success will be 0.09, and then will be true. And though that will give us 0.872306, and then we use the complement rule. So 1 minus that number equals 0.1277. Let's continue on with the binomial distribution and calculate the mean and standard deviation. So we have P is the probability of success. We've been working with that already in the prior slide. So now we need to calculate the probability of failure, or Q, which is just simply 1 minus P. And then we have our sample size. So now we're going to calculate the mean, or the expected value. So the mean is going to be N times P. So that's going to be 30 times 0.09 equals 2.7 packages. Now the standard deviation is going to be the square root of N times P times Q. So this is going to be the formula in Excel. It's going to be equals square root 30 times 0.09 times 1 minus 0.09, which is 0.91, equals 1.57 packages. Let's walk through a Poisson distribution problem next. So we have a situation where cars arrive to a bank ATM drive-through, and they arrive with a mean of 4 cars per hour. So there's two things you want to do first. You want to identify the segment unit. So we're told that the cars arrive per hour, so that segment unit is going to be 1 hour. Now lambda, or the mean, is going to be 4 cars per hour. So in problem A here, what is the expected number of cars arriving in 2 hours, or lambda times t? So we know lambda is 4 cars, and then we're told it's now 2 hours. So the expected number in 2 hours will be 4 times 2, or 8 cars. Now we're going to calculate in B the probability of 6 or less cars arriving in 2 hours. So we're going to enter Poisson.dist. We're going to enter 6 for X, since we are including up to 6. Then in Excel, you want to remember that the input is lambda times t. So you're not going to be using 4 cars here. We're going to be using 8 cars. So 8 is going to be the mean, and then we are calculating our probability up to 6. So we're going to use true for cumulative, and we get 0.3134. So in C here, we want to know the probability of 9 or more cars arriving in 2 hours. So similar to the last slide, we need to first use the complement rule. So we're going to have 1 minus, then Poisson.dist, and we're going to calculate up to 8. So we're going to use 8 for X, and then we'll use our lambda t for mean of 8, and then true for cumulative. That's going to give us 0.592547. Then we use the complement rule of 1 minus that number, and we get 0.4075.